Okay, so very sad story. The video from Friday's lecture, I basically sabotaged because I tried to correct a mistake and I ended up losing the entire video. It's entirely my fault, but now I'm going to try and recreate that video. I'm not going to recreate the notes. I'm rather going to just talk through what we did during the lecture. So first of all, if you check out page, 55, I think, there's a box there. Yeah, 55. And it explains how to use Jacobians in double and triple integrals, which is what this section over here is talking about in the notes. That from all that stuff that we did early on with linear transformations and what the geometric effect of linear transformations on things like a unit square or other areas, you end up with your old area divided by your new area is equal to the determinant of the matrix that represents the transformation, which for nonlinear, well, it's always your derivative matrix. For a linear transformation, your derivative matrix is just numbers. Of course, it isn't for nonlinear transformations. But you end up with this relationship such that the delta area old is equal to a particular Jacobian times the new area, the new delta A, where the Jacobian will have your original variables, the ones you started with at the top, differentiated with respect to the new variables, whatever they happen to be. So it's very important when you put in your Jacobian, that's essentially a conversion or a scaling factor between the two coordinate systems, that it's the right one. It must be the derivative of the old variables with respect to the new variables. There are some examples, which we'll see below, where it's the Jacobian that's the obvious easy one to work out is actually the other one. It's d new by d old. But that's fine. You work that out and then you just flip it. You find out the reciprocal. You work out the reciprocal for your purposes. Okay, what did we move on to after that? Okay, I demonstrated with 3 examples, 92, 93, and 94. And they're all slightly different in that they all trigger the use of a coordinate change in different ways. In 92, what we have is an integrand that has an x squared plus y squared in it. Whenever you see x squared plus y squared in an integrand, you should at least pause to consider that polar coordinates might be useful, because x squared plus y squared gets replaced with r squared, which is very convenient. However, if then in this particular example, 92, your region is very much conducive to using polar coordinates. In the lecture, when I drew this picture, I carefully worked out what the coordinates of that intersection point were, because I wanted to does in fact give me that entire shaded pizza slice sort of shape. And once I had determined that these limits here describe this over here, this what I'm calling pizza slice area, this sector, then that is immediately a trigger to conduct a coordinate change and to talk about r and theta instead of x and y, because in this shape over here, the sector, you have r going from 0 to root 8 is the radius of your circle, and theta going from pi over 4 to pi over 2, because this angle over here is pi over 4, and then this angle over here is pi over 2. So you can see limits of integration for r and theta are just numbers, which makes everything so much easier. The limits of integration have to become r and theta limits of integration, and you must get your Jacobian, which we derived yesterday on Thursday, and that's Jacobian. Okay, once you've got constructed that double integral, the actual integration is pretty easy. It's just straightforward integration. I jumped straight when I did this into integrating to recognizing that r over 5 plus r squared is the derivative of this log. If you didn't recognize that, then going for substitution is a good idea. U equals 5 plus r squared. So basically, the integral integral. It forms part of the integrand, and we take it into account when we integrate. Okay, so 92 was an example of it being primarily the region that prompted a coordinate change, specifically a polar coordinate change. Okay, let's move on to exercise 93. Okay, so in exercise 93, our region is this triangle over here. Okay, it's described to us, we're told it's a triangle and there are 3 vertices, and that region is a very simple region. The region itself really doesn't suggest doing a coordinate change. However, our integrand does. Because if you ask yourself, what did I differentiate with respect to x or with respect to y to get this integrand, I think you're going to struggle to answer that question. So what I did, a substitution. I made it is a substitution, but I'm basically carrying out the transformation u equals x plus 2y and v equals x minus 2y, and that way this x plus 2y turns into v, and this x minus 2y turns into v, and now my integrand is very much simplified. My dA is going to be dv du and the Jacobian. Jacobian come from. I have a transformation that I have designed. It's not like polar where we have the Jacobian memorized. We're going to have to work out the Jacobian. So we work out duv by dxy. This is the obvious Jacobian to work out because we have u in terms of x and y, and we have v in terms of x and y. It, however, is not the Jacobian we want because u, v are the new variables and x, y are the old variables. So ultimately we're going to work out this Jacobian down here. Okay, so the Jacobian is a determinant. First of all, when I was doing this in class, I just wrote this in the black ink, and we ended up with a determinant of minus 4. Now, determinants can always be negative. Jacobians can always be negative. If we're putting the Jacobian to use in this context of converting between 2 areas, we want the magnitude, we don't want the sign. So I put in the red absolute value signs, and notice how I put them in all the way back. You can't just put them in at the end. Okay, so at least the absolute value of minus 4 is the Jacobian that we've worked out, but we actually want the reciprocal of it. So in other words, we've got a quarter, and that quarter goes in here. Okay, we also need to work out our new region. Because our transformation is a linear transformation, our triangle is going to turn into another triangle, and all we need to do is figure out what happens to the vertices. So one by one, we plug in our vertices. So x equals 0, y equals 0, we plug into the u and v expressions, and we get a u value and a v value. We do the same for x equals 0, y equals pi, and the same for x equals 2 pi, y equals 0, and we get a uv, and we get a uv, and those 3 points we plot on a uv picture, and we can see our new triangle. Okay, so this is the region that we're going to integrate across. It makes sense to do v first, because v goes from the one oblique line to the other oblique line. If we did u first, we'd have to split it up into the sum of 2 double integrals. Okay, so we need to work out the equation of this little oblique line and the equation of that one. Because we know the coordinates of the corners, we can work out that this is v equals u and this is v equals minus u. See, this is quite a lot of work goes into this whole setup, until finally we're ready to construct our new integral, which has a dv du, it has the Jacobian, which I'm going to call out. My integral is nicely simplified. Here I have minus v minus u, and v minus u represented to y, and to now integrate. And so step by step we integrate. Over here we have sine squared. When you need to integrate sine squared, you use your cos double angle formula to turn it into a double angle instead of a square of a trig expression. And bit by bit we end up doing the integration. Okay, so if this were being marked in a test or an exam, let me go right back to the beginning. There'd be marks for, there'd certainly be a mark for your UV picture, possibly not for your XY picture. But there definitely would be a mark for your UV picture. There'd be a mark for coming up with a sensible transformation. There'd be the mark for working out the Jacobian. There's a little bit of a break there because somebody came into my office to talk to me. Where was I? We were talking about Jacobians. I've lost track of where I was. Let's have a look. Oh, I was talking about marks. So there'll be a mark for the UV picture. There'll be a mark for the transformation. There'll be a mark for working out the Jacobian, and also another one for inverting. So, but of course you did also have to take the modulus, but roughly speaking there'd be about 2 marks for this section over here. Then, of course, there would be probably 2, 3 marks for putting everything together in there, and then either 1 or 2 marks for doing the calculation. For this example, probably 2 marks because you had to use this trig identity. So yeah, these problems are always very mark heavy at the top. All of the setup stuff is where most of the marks are. So one should learn mathematics for its own sake, and you should learn mathematics in order to use it in various contexts. It's pretty unpleasant to learn maths in order to pass a test. It's not really a nice motivator, but we live in the real world. We know you do have to write tests and exams, and we also know that sometimes people run out of time. So if you tend to run out of time and you need to be strategic about your choices, once you've got to about this point here with your setup, leave a nice big gap, come back later. You could be losing 1 mark, 2 marks, maybe if it's a really tough integral, 3 marks, but you'll still have gained the bulk of your marks. And maybe if you move on to another question, it might be time better spent. That's completely up to you. Everybody is different. And yeah, you just have to make your own choices. I'm just making you aware of the fact that these problems are always have the marks bunched at the top. Okay, all right, then moving on to number 94. Now let's have a look. 92, it was the region that triggered a coordinate change to polar coordinates. 93, it was the integrand that triggered a coordinate change, one that we designed to fit that particular problem. 94 is similar, that we are going to be designing our own transformation. It's the region, because the curves that we were given were 2 hyperbolas and 2 parabolas. And that's our region. That's the region that's bounded by those curves. And that's an appalling region to integrate over if we stick with our rectangular coordinates. So what we're going to do is we're going to design a transformation, and we'll take advantage of the fact that the equations are paired. We have these 2 hyperbolas that are clearly a pair, and we have these 2 parabolas that are clearly a pair. Okay, here we have something to do with variables equals a number, and here we have that same something to do with variables equals a number. We've got xy equals 1 and xy equals 5, and over here it's a little bit messier because we've got variables on both sides, but we can bring them together. We can say y over x squared equals 4 and y over x squared equals 1, and now we have our 2 parabola equations following the same pattern as our hyperbola equations. Variables equals number, same variables equals different number. Variable equals number, variables equal different number. And so I've made the transformation of u equals y over x squared, and that goes with those two, and v equals xy, and that goes with these two. Okay, in other words, we have a new region in UV space where U goes between 1 and 4, because here we've got U equals 1 and there we have U equals 4. And V over here, V goes between 1 and 5, and so we have this new region. Beautiful, simple region. So our limits of integration are going to be all about U and V. So we have Jacobian. So let's work out the Jacobian. duv by dxy is, and we very carefully work out our derivatives. That's a derivative of u with respect to x. Derivative to y, derivative of v with respect to x, to y. Crisscross determinant, and we end up with that. Our original region, the one full of x's and y's, is in the first quadrant where x and y are both positive. So we can be confident that this result over here is definitely going to be negative, and we're ultimately going to want to take its absolute value. We could take its absolute value now As long as you do it eventually, that's what matters. Of course, do you identify where the Jacobian or not? Because this is new variables and unknown variables, and we can't already know. So we want to integrand. Okay, here's my comment that it's negative and we want to take its absolute value. The absolute value. I flipped it, absolute value, and now I'm recognizing of course here is 1 over 3u because u is y over x squared. Okay, now we're ready to actually construct the integral. Here it is, and we're running out of time in the period, so I'm just doing the solution. We should find that a fairly easy integral to solve. Okay, there's only one thing I can remember that was important. Of course, I always get sidetracked, but one important thing I mentioned during the lecture, and one recorded here on the video, is in general, we want to change it to have the variables that are actually the ones of interest in our integral. Sometimes that can be quite hard to do. So there are occasions where you can actually keep this as x's and y's and put it here. So we could have kept x squared over 3y here. Of course, as long as there are x's and y's there, we're not yet ready to integrate because the integral is only interested in u and v. But sometimes what you end up it cancels with your new Jacobian and relieve you of the pressure of having to change xy Jacobian into a uv Jacobian. Those are fairly unusual, but there is an example like it in the handbook. I believe it's 96. So if you're really struggling to turn your xy Jacobian into a uv Jacobian, at least spend a moment to check to see if you plug it in with x's and y's still in it, does it actually cancel? Because that is a possibility. If it doesn't, then you just need to be creative and somehow make this using these, because you can't actually integrate while x's and y's are still there. Okay, I'm just going to pause now while I think if there's anything I've forgotten. Okay, I sat here and thought for a while to try and remember anything that I mentioned during the lecture that I haven't recorded. There are quite a few questions during the lecture, but I think I've covered everything. Okay, so I'm sorry about the fact that I don't have the original video. I know exactly what I did. I was just a bit of a twit. I hope that what I've done here has been explanatory enough that if you want to dig into this stuff over the weekend or later, that you can follow what's going on. If you have any questions, of course, you're welcome to ask me, and I'll see what I can do.